Welcome back to the course entitled Chemical Crystallography. In the previous weeks, we have discussed about the theories of X-ray diffraction, and then I have demonstrated how one can use Bruker's single crystal X-ray diffractometer to collect the data. Then in one of the lectures, we have discussed how you can process the X-ray diffraction data, do the structure solution and refinement. So in this particular lecture today, in the 12th week, I am going to demonstrate a condition where the crystal is not a single crystal. Actually, this data was collected on a sample of 2,3-difluoroaniline, which is liquid at room temperature, and this compound was filled in a capillary and cooled below its freezing point. Crystals had formed, and using optical heating and crystallization device, we have converted that polycrystalline material into partially crystalline or crystalline material, which probably still contains more than one crystalline domain in front of the X-ray beam. So when we try to do this indexing, you will see that this crystal does not give any specific unit cell parameter, and it gives very poor fit for indexing this pattern. So I am now just loading the images. When you look at this image, you see that these reflections look like this is a single crystal. It is not looking like a polycrystalline messy substance. So if we try to read these reflections, we will try to read one set of reflections and total about 200 images with I by sigma equal to about 10, so that we take care of large or small reflections, or that is strong or weak reflections. So when you try to read that, it will take a while to read these reflections from 200 frames that were collected during the data collection procedure. Once it completes harvesting, it will allow us to do the indexing. So now it is letting us do the indexing. I am saying that you use all the methods that are available for indexing and then try to index the pattern. You see the first method has failed, second method has also failed, and third method is struggling. It is not able to give anything. We cannot wait for infinite amount of time, so we click cancel. What we have here is 804 reflections that we see in this particular set of reflections. So to view these reflections, one can go and click on edit. You will see all the parameters related to these reflections as a list, which are essentially meaningless at this moment, because these are numbers where the reflections were found, the value of omega to theta, phi and chi and so on. So from this we have to get the unit cell parameters. So we want to see these reflections in the reciprocal lattice viewer, which is here on the left hand side of the screen. So if you click on that, it will open the reciprocal lattice viewer and it will show all those reflections which are shown in gray. So now what we see here is that if we do not have any intensity filter, we see that there are two sets of reflections going like this, which essentially means there were two crystals in front of the X-ray beam and both were diffracting during this data collection. So what we need to do is to separate these two sets of reflections coming from two different tiny single crystals present in the beam. And this RLAT is a very efficient tool in doing so. So first thing that we need to do is to remove the size, reduce the size of the reflections so that the overlap region is reduced, and then we sort of zoom it in and try to see in what plane they are nearly matching. The ones which are completely out of those planes, we want to throw it away. So we will do a lattice overlay and take from here to this point, and we will press the button plus. If you press the button plus, you see this window gets splitted into parts, and it gives you lines parallel to the lines where the reflections are sort of aligned. So now if we release the mouse button, these are now selected. I want those reflections to stay and others to disappear. So we do invert selection. So now the selected ones are deselected and deselected ones are selected. And then we change the group to green and say that send selected reflections to current group. So those reflections which were selected are now in green. So now if we untick this, the green reflections which are totally out of the world are now removed. So now we go back and use the rotation tool to rotate X and Y. Now it is very clearly visible that there are two sets of reflections in two different directions. So now we again try to align these reflections in such a way that somehow we can take one and remove the other set of reflections. So now we go back to our lattice overlay tool, start from one end and come to the other end as much as possible, and then once again press the plus button to align some of these reflections along the lines. We can press the page up button to expand on either side to include those reflections which are coming beyond our lines. Now again we invert the selection and save it as a different group called yellow. So now if we deselect the yellow group, we have a series of reflections which are now aligned. Still there are some reflections which we see here are not exactly falling on the line. We then again try to do the same operation from this to that. To reduce the number of lines, you press the minus button and then again do this adjustment from one end to another. And then start making it plus till these lines match, and then add page up so that the other sides are taken, and then again do invert selection and send the ones not selected. Send the ones which are selected to yellow and the other ones will remain as gray. So now we have a series of reflections which are matching. Now if we just look at yellow and remove this gray, we see that they are also matching in line along with other reflections. So technically we have two crystals identified, and there are some in between reflections in this YOLO as well. So we should specifically remove those reflections as well. So again, to reduce the number of parts, we should press minus, take the two ends and then press plus till it matches the lines. Then you go page up and include the reflections on either side and do an invert selection. And sorry, I made a mistake. Invert selection, and then I should have clicked different. So we do it again. Page up. Invert selection. Make it green and throw away those reflections in green. So now we have two sets of reflections. One is YOLO, where still we see one reflection is not online. A single spot can be selectively removed. This one can be selectively removed. And we look at these in different directions to see if there are any unaligned reflections, which is here. These reflections that I am removing are not parts of any of these two sets, the yellow set and the gray set. So we need to check this for both the gray and yellow, and we'll rotate the reciprocal lattice in all possible directions to see if there are any reflections which are not aligned with the other reflections. Right? So now we have two sets of reflections, yellow and gray. Now we go back and try to determine the unit cell. You see that 804 reflections are now splitted into gray, green and yellow. Green don't correspond to anything. We will worry about it later. The gray and yellow corresponds to some unit cell. So let us now try to index with the reflections which are in gray. Now you see it is very easily giving the unit cell as 4, 9, 14. The second method also has given 4, 9 and 14. Third method sometimes struggles, but it gives a different unit cell with a different figure of merit as well. So by default, the top one is taken as the unit cell. So we set the tolerance to 1 and refine a few times. What we see that the standard deviation on the unit cell parameters are in the second to third decimal place. So then we accept this and go ahead and identify the lattice type. You see it is giving us 90.2 with monoclinic and orthorhombic as like this 89.8. At this moment I would prefer the monoclinic because it has a higher figure of merit, and 90.2 is a significant deviation from 90. So by accepting this, again we should do the unit cell refinement and do it a few times and accept it. So this is the unit cell corresponding to gray. Now I take this yellow and index it, and of course now since we are not considering green, the next indexed pattern will be in green. So now with those yellow reflections, it is again giving the same unit cell 4, 9, 14, right? then it gives something else, and again 4, 9, 14. So 4, 9, 14 is probably the correct unit cell. You make the tolerance again to 1 and refine a few times to see the ESD is coming down to the third decimal places. Then again we take the monoclinic P. Here it gives you 90.24. Define it once again with the tolerance 1. So now we have two unit cells from gray and yellow. Both are giving us about the same numbers in terms of unit cell parameters. So this clearly tells that now we have two single crystals inside the lattice, inside the capillary. So now if we go back to the reciprocal lattice viewer, remove both gray and yellow and take the green ones and try to see, is there any sequence, or is there any what I would say is alignment of reflections. What we see is, yes, there is some kind of alignment of reflections. So this essentially indicates that there may be a third crystal present within the beam. So I am not going to consider this and make things complicated. Of course, it looks like there is a third crystal present in this system. Right? You see, there is alignment. So it is a mixture of three crystals. So I will now go and try to do the data reduction as usual. But here, what we will do is we will select the runs. We have here two sets of runs. So we will take those two sets and refine them or integrate them in a folder called, instead of var, I will call it as 1, and here also it is 1. That is the first unit cell, that is my gray unit cell. And we will start the integration. So what it will do is it will read 1200 frames from each of these sets and use the matrix, use the indexing matrix from the gray unit cell and give you the data reduction files in the folder 1. So let us start the integration. This integration will take a while, because you see this will read 1200 frames from each of these runs and then extract the data from those 2400 frames. And in front of you, you are seeing the data reduction process is going on, and it continuously calculates several parameters related to this data reduction process. So now we see that the integration has finished and it says new orientation matrix has been written and these plots have stopped updating. So now if we close this, we can see the integration result in detail. So this is the final unit cell in which it has converged, and this is the reflection statistics that it has got. What we see is that the percentage completeness is very little. Percentage completeness is very less than 80%, even at 0.85 angstrom resolution. So what happens in this case is the number of reflections that were obtained from one set of unit cell is not, one set of crystal, one particular crystal is not enough. So we close this. We would do the data reduction once again with the green unit cell and save that data in the folder which we name as 2. Why are we doing this? Because we want to join at the end the reflections coming out of two different crystals of the same compound that were exposed in the same machine at the same time inside the same capillary, and they have received the same amount of exposure time for data collection. So we can merge these two data sets originating from two different crystals using a software. So again I am starting this integration using the unit cell that has come in green. So now it has completed the integration of the second data set as well. So we just close this, and what we need is now to go to the folder to take the raw file of 2 with a name. Instead of 0m we write it as 2m, and take that raw file in the folder 1, because we will read the folder 1 in the next step and then add this data at an appropriate point. So we need to do a scaling. When we try to do scaling, we need to allocate the starting folder. So we will use this folder and we will take this 0m.raw, which is the raw file of the first set, and then we will start. This is a standard procedure as we have done for a normal single crystal. You do it one by one. If you want to refine these parameters, you can do it again with little change or no change. Then we go to the next step. It will then give us the R-int values. You see the R-int is quite good. And then we finish it. So this scaling is done for the first data set. Now we should go and look for something called XPrep. This XPrep will now read my HKL file in the set 1, because now the raw file after scaling is converted into HKL file. So now I am going to read that HKL file with the 0MP4P, which has the information about the unit cell parameters of the cell gray that was determined in gray color. So now we have this window of XPrep, and in the past we have shown how this XPrep can be used. So here I am going to continue. H means search for higher metric symmetry, and then here it says it may be orthorhombic. At the moment, now let us assume it to be orthorhombic, and then space group, orthorhombic, primitive, and it then says it may be PNA21 space group. We accept it, and then it is D, which means read, modify or merge datasets. This is the point where we should call our other data, which is the data from the yellow crystal. So here we can read another dataset by typing R. And here it is refined, or it is asking what was the cell settings. It is the original cell settings, not the current cell settings. Now it needs the file name. What is the file name? File name is 23DFAN 235K underscore 2M.raw. So this is the file name it is supposed to read, because this is the file which we copied. This is the 23DFAN difluoroaniline 235K underscore 2M.raw. It is in the HKLF4 format, and we just continue. So the new dataset has been read, and now if we click L or write L, it will do least square, scale and merge datasets. So it will merge these two datasets. Here we always use isotropic scaling factors. Dataset index is 1, enter, 2, enter, and there is no further data, so we just enter, it will come out. Now it is asking what are we supposed to do? Create a new merged dataset or replace the old dataset with a single scale but unmerged data. It is always advisable to generate the merged dataset in case when you are joining two or more datasets. It is asking, should we merge the Friedel opposites? You have option to give yes or no. The default option is no. So here also we say that no, don't merge Friedel opposites. So now what we see is that the two files which has RINT values of 0.75, 0.75 and 0.46 are going to be merged, and the overall RINT is going to be 0.616. So now I have a merged data with 1241 reflections. So now if I do a intensity statistics, still we see the overall completeness up to 0.72 is very less. We try to cut this data at in resolution of 0.84 or maybe 0.83, and see what happens. See, up to 0.83 the completeness is about 80%, which is not that bad. So we come out of this and then determine and then incorporate the unit cell contents. Since it is difluoroaniline, we have C6, H3, H5, N1, F2. Now, as usual, it generates the standard output file. We write it as 23DFAN235K is the name of the newly generated file. So now it has generated the new HKL file. We try to open OLEX2. And solve the data that we have reduced from the crystal, which was technically not a single crystal, which was a crystal containing 3 crystals inside. So as usual, using OLEX2, we should locate our data set. And you remember we have the data final thing in folder 1. So this folder 1 contains our final HKL and INS files. So we choose the INS file. It reads the data from the INS file. We go to work. Under solve, we have the standard modules and we click solve. So it uses ShellXT, which is the method of intrinsic phasing, and tries to give you the structure solution. You see, in less than 1 second, it has given us the structure. One can identify that as nitrogen, and we try to refine it. One should actually increase the number of cycles to 10 and number of peaks to about 20 and say refine, with the weight factor being refined continuously. We also activate actor here, otherwise we may forget at the end. So what we have is the crystal structure of difluoroaniline, isotropic refinement, and then I am doing anisotropic. You see now the hydrogens are appearing. If I make it 5, you will see that just the hydrogen atoms that are connected to these carbons and nitrogen are appearing. One can easily identify those and set as hydrogens and refine. So by clicking OK, it gives you the correct formula, and a few rounds of refinement will convert everything into green. The points which are orange or red here are the problem points, because the data is not a very good data, the crystal did not diffract, and the standard problem of in situ crystallization is that we cannot rotate the kappa during the measurement, and that is why the completeness is always less. But what we can show you here, the crystal data which was not possible to index using a normal procedure, the structure can be solved if we follow this method. Now what we see here is, although those hydrogen atoms were coming up, the bonds are not at 120 degree and all that. So it is always advisable not to refine hydrogens, rather fix those hydrogens using the riding model for any routine X-ray diffraction data. So we do a few rounds of refinements, and at the end of that, all this will turn out to be green, and there is no alarm or alert that is coming here. So I would say that the structure solution and refinement is complete at this point. Hope you have learned a technique, learned a method to index and finally solve the crystal structure of a crystal which essentially was not a single crystal, was in this case there were multiple crystals. In some other cases it can be a crack in the crystal that you have selected, or it may be possible that you have mounted a crystal thinking that it is single, but there may be a very, very tiny single crystal sticking to your larger crystal, which could be missed under microscope, and then the diffraction data shows the presence of another crystal on top of your crystal. You can use this method to segregate the reflections coming out of two different crystals, then reduce the two different data sets separately, and then join one data with the other using the X-ray package available within Blue Card diffraction software. So hope you have learned something, and it will be useful for all of you. So thank you. There are couple more lectures in this course left, where we will learn about polymorphism and its applications. So stay tuned, we will have 2 more lectures before the course concludes. Thank you.